And ladies and gentlemen, we now go to the Americas. We have a final set now of blueprint cases, and they are all joining us virtually in this session. And I am just going to remind everybody while we get ready that the US government, of course, as we heard earlier today, has recently boosted its own support with the launch of AM Forward, which is a compact amongst large manufacturers that is aimed at putting additive to work and enhancing the resilience and competitiveness of US supply chains. So our speakers are with us now, and it is my great pleasure to introduce all of them, and then I will call on them to give us their presentations, beginning with Melissa Orme. She's a regular here at AMTC. She's Vice President of Boeing Additive Manufacturing. Great that she is with us now remotely. We will hear after that from Bill Haddad. He's Director of Additive Design and Manufacturing at Collins Aerospace. He's also with us online. And then finally, Jason Carroll will tell us about his experience, Vice President of Global Technology at the US-based globally active power management company, Eaton. And he too is with us virtually. And I'm just going to remind all of you before I hand over to Melissa that we are looking for you to share concrete examples of what you're achieving with AM, as well as some of the challenges you faced and how you solved them. Also, key drivers that are helping you integrate and scale AM and how you're approaching collaboration. And all of that. And then, if you would, please keep it concise so that we can take audience questions afterward. Thank you so much. And now, please, Melissa Orme, over to you.
Hi, thank you so much. And it's really good to see you again, Melinda. And sorry I'm not there in person. I've always enjoyed your conference. I've talked several times at Oerlikon, and I've already presented, the many things that Boeing is doing with respect to additive manufacturing in terms of use cases. Right now we have thousands of parts in flow in different part of our, value stream for insertion onto Boeing products. So this time I thought I would do something a little bit different. And I wanted to talk about additive manufacturing as a sustainability driver and to provide one use case study there. So I will just see if I can handle the clicker. Yep, I can do that. That's great. So, Boeing has committed to decarbonizing aviation. And we've basically committed to doing this through advancements in technology, such as additive manufacturing, among many. Advancements in operations and infrastructure, sustainable aviation fuels and carbon offsets. And specifically, Boeing has committed in numbers to reducing greenhouse emissions by 25%, water consumption and solid waste to landfill by 20%, energy use by 10%, and hazardous waste by 5%. So in my organization, Boeing Additive Manufacturing, which we also call BAM, we have also aligned our sustainability goals to exactly these measures. Notice I don't have numbers there yet because we didn't have quantitative numbers. And this is really something that I wanted to do instead of just, waving my arms and saying that additive manufacturing is a positive sustainability driver. I really wanted to get some data. And so we finished our first case study, and this is what I'm going to talk to you about today. Additive manufacturing, I think we all understand, uses less material than for example, traditional manufacturing processes, especially things like, large hog outs. And so you see here I've written down, the additive manufacturing sustainability benefits, and these are not all. You'll think of more as well. But basically, we create less waste. We use less material. And there's two reasons for that. One is because of the intrinsic nature of additive, where we use very close to only the material that we need. So if we're just doing a part for part swap where we haven't changed the design, we're using a lot less material. But then there's another way as well. We go a step further, and then we can optimize, because of additive, we can optimize that part and lightweight it and even use less material. So we have less waste generation. Design optimization, I think we all know that we can lightweight parts and integrate assemblies. So we can reduce the actual operations of assembly by integrating parts together. And we eliminate not just the parts, but all of the processes that go with those parts, the procurement of fasteners, the testing of the other parts, the transport of all those parts. We reduce that, and all the energy consumption that is coupled with that. We eliminate primary tooling, and that's the labor, the time, and the cost, and the materials and energy. Reduction in transportation, that's the raw material transport, that early end of the early stage of the value stream, the mining of the material, the converting of that material to a printable material, and the transport of that material, that's greatly reduced. And then all the other reduction in transportation, the subcomponents that we've eliminated. And I'm kind of using that flippantly, like we can eliminate parts. I'll give you an example. We have one product where we have in heritage fabrication about 41,000 parts. These include fasteners, secondary piece parts. We have redesigned it to have a little over 1,000. We've reduced about 42,000 parts. Okay, so when people ask me how many parts are you printing, Melissa, I say you got to flip the question into how many we're eliminating. And when we eliminate all those parts, we eliminate all of the processes, not just the overhead. I should say the energy overhead, right, with respect to quality, procurement, testing, transportation, and let alone the energy in creating those parts and materials. And then the last part, in inventory waste reduction. So due to the ability, to create spare parts on demand, we're not inventorying large amounts, and as I said before, the elimination of major and minor parts due to consolidation. Those parts don't exist anymore, so we're not inventorying them. So we did a life cycle assessment with these 5 key areas where we looked at the raw material extraction and conversion for both the heritage part, the traditionally manufactured part, and an additive part. We looked at the energy consumed, water consumed, protective gases, things like that, for both ingots as well as wires or powders. Then we looked at the manufacturing process, and we measured the materials consumed, the gases, energy, water, and hazardous waste. And then we looked at the transportation, as I just discussed, and the energy consumed in the distribution of the raw materials, the procured parts, assembly, sending things back and forth for testing, recycling the materials, waste disposal, and then transportation to the final end user. The usage and the waste disposal, end of life, material recycling, reprocessing, and recovering. So these are the attributes that we looked at for our case study. And this is the part that we did. And this is a tie wire part. It's one of 7 additively manufactured parts. That's in every 787 since 2017. So prior to 2017, these were machine hog outs out of titanium. After 2017, these are tie wire. So we have data for both cases. And so we did this life cycle assessment for this particular case. And it's not been optimized, so we don't get that secondary benefit of further lightweighting and things like that. But just a part swap out basically from traditional to additive. And this is what we find. Oops, my light just went out. Excuse me. So we have there we go. The titanium additive manufacturing versus conventional. So we have the 5 key metrics that we've aligned to our Boeing goals: energy consumed, global emissions, solid waste to landfill, hazardous material use, and water consumption. And the blue in that pentagon shape is the traditional case. The orange is what we measure in our additively manufactured case. So you can see in every single attribute, we're significantly lower. So we've really reduced the harmful environment and human impact. And on the right-hand side is me trying to tell you why. And it's really for this particular part, the raw material resourcing was really the major driver, and then the machining resources and that scrap. And even though the additive manufacturing process has pretty high energy consumption, and we had to use argon gas shielding, and we had to stress relieve things we didn't have to do otherwise, that was still accumulatively much less than the conventional manufacturing drivers. I'll interject here that this, won't be the case for every modality, every part. The particular case that we've decided to study first has this really great attribute. And one of the things that we're doing now at Boeing, we're doing a case study for powder bed fusion and a manifold that's typically cast, and then another powder bed fusion for like a sheet, what's typically a sheet metal bracket. And giving away the punchline in advance, we'll find that the sheet metal bracket is going to be a horrible, will have a really bad sustainability, impact. And it's best to just, produce that part traditionally, which it was just something that we really want to know. And what will be interesting, and it kind of aligns to a question I just heard in the last panel, is that I believe what we're going to find is that the parts that that don't have a good sustainability trade also don't have a good business case. We have no business, I think, additively manufacturing sheet metal brackets, right? Because those are going to be a lot more expensive anyway, and they're going to consume a lot more energy, as I hope to show you maybe next year with the other case studies. But anyway, part of our goal at Boeing is to define a strategy around additive manufacturing and sustainability, and define when we will actually employ additive manufacturing for our sustainability contribution, and when we won't. So we all, going back to the presentation, we looked at other drivers, and these are, some call them secondary, but I think they're also really important. And these are basically, human toxicity, both carcinogenic and non-carcinogenic attributes, acidification, ecotoxicity. I have some definitions on the side of what these are if you may not be familiar: abiotic depletion and eutrophication. And you can see, again, the additively manufactured part is always significantly lower. So it's really is reducing all this, the harmful impact for the environment and to humans. And so there's a few other things we can continue to do. Really being mindful of how we recycle our powder, be pretty smart in how we nest things, for example. The little part I'm showing in the second column is a AMOS command horn antenna that was launched on a satellite in 2019. That's a redesign from a traditional part, which had many fasteners and so forth. It was designed as a monolithic part, but I really like this part because it was designed not needing a single support structure. So we've got to get smarter with respect to support structures and designing for no support structures. I think many times that's possible. And also simulation guided builds, make sure that we get it right the first time. This is something that's part of our value stream. Machine utilization, we're doing some studies. It looks like, those, multi-laser machines use a lot of energy, but they go faster. So many times it's beneficial to use those. We'll actually use less energy, holistically. Post-processing optimization and nesting things, and CT scans and heat treatment, and finally, sustainable energy sources for operations. So this and other things, we're always looking at how we can even be better. And I like to close with a quote. I think it's really important. I like this one: "A society grows great when old men and women plant trees in whose shade they know they shall never sit." I think this is really important because it really points that we don't do this right now for ourselves. We do this for future generations, to make sure that their world is a better place. So I will end that there. I think I'm about 1 minute early, probably unusual for these kinds of talks, but thank you very much.
Thank you. Thank you so much. Melissa, you're getting a lot of good applause. I hope that you can hear it. And that's 1 minute more that we'll have for the Q&A afterwards. And you've also provided some great input for the sustainability session that we're going to do at the end of the day. So much appreciated there. Please stay with us because we will come back to questions and answers. But first, I want to go to the other presenters. Up next is Bill Haddad for Collins Aerospace. Over to you. The floor is yours.
Thank you very much. Good morning, everyone, or should I say good afternoon. It's a great pleasure of mine to be joining you virtually and to be sharing the stage with the virtual stage with Dr. Orme and Dr. Carroll. I'm going to run you through a quick use case. I heard the instructions earlier to leave plenty of time for Q&A, so I hope to be able to do that. So I'm going to talk to you today about a conformal heat exchanger that then UTC, and I'll talk to you about the name change on a subsequent slide, but then UTC, now Raytheon Technologies, of course, produced in conjunction with America Makes back in probably the 2018-2019 timeframe. And some of you may have seen this published in Metal AM. So some of what I'll present to you may be familiar to some of you, others hopefully benefit for the first time. So back in 2015, America Makes did launch a project to produce via laser powder bed a heat exchanger in conjunction with DoD and AFRL. Again, the name change, right? So at the time, we were known as United Technologies. So what was known as the United Technologies Research Center, now Raytheon Technologies Research Center, partnered with my business, Collins Aerospace, with what was known as the UTC Additive Manufacturing Center of Excellence, now the AMPCC. We partnered with Pratt & Whitney and two external organizations, Stratonics and 3D Sim. And really the project goals here were really to do a number of things, to prove a number of things, but ultimately to demonstrate new capabilities and new processes with respect to heat exchangers. And for those of you who are familiar with Collins Aerospace and throughout our history, thermal management has been a strong component of ours, a strong technology of ours for decades. And so obviously taking that core competency and now applying all the wonderful benefits of AM is certainly something that we continue to do throughout our corporation. And so it was a natural fit for us to get involved and to jump into this project. A few other things, obviously we were working with Inconel 625, which is certainly a material that all of us know quite well, especially in the aerospace industry. And this project duration was quite long. It was about 3.5 years. So while the project got started in 2015, we ultimately didn't deliver the final heat exchanger until sometime in 2019. So speaks a little bit to the persistence, and we'll talk a little bit about lessons learned later, but the persistence and really the focus of operating in an environment like this across a long time. So for the conformal heat exchanger, we took what we thought was a pretty novel approach, right? And at the time, if you remember back to where we all were in our additive journeys back in 2015, some of what we might look at today as pretty normal or standard at the time, I think, was fairly cutting edge or was fairly groundbreaking. So using some of the predictive tools, not only for process but also for performance of the part, I think at the time was fairly innovative. And what you can see from the graph there is, it's really about the machine default parameters. Again, at the time when some of the machines didn't have the capabilities that the wonderful OEMs are producing today, we really needed to look at customized parameters. How could we work with the machines and all of the parameter sets in order to design parts, in order to produce parts that really got down to some of the features we needed. Obviously, for those of you who understand, heat exchangers and their performance, surface roughness is a huge aspect of all of the subcomponents, the fins, the plates, et cetera. And so working with customized parameters was very, very important to us. We took a physics-based model approach. So we really wanted to look at, the performance of not only the final assembly, but the individual components. That was very important to us. And what we did from there was we we developed a customized solution for each section of the heat exchanger. So how we attacked the fins was different than how we attacked the partitions, was different than how we attacked the headers, because each of those parts have different performance characteristics. Each of those sections have different requirements. And so a one-size-fits-all approach was not going to optimize the performance of the part. So again, a key learning here was customize your build, customize your strategies for each section of the part, whether you're building a heat exchanger or a housing or landing gear, whatever you may be building. Look at it for each individual sections and really attack them individually. So I mentioned the physics-based modeling a few moments ago, and really we took a look at some of the different approaches for the different components, like I said, but also how we looked at the machine material combination, right? So building a customized print map that you can see down on the left side, where we were able to work with the machines and find our sweet spot, if you will, where the combination of laser speed and laser powder, which gave us the best output, the best outcomes inside of the build chamber. Obviously, with respect to the heat exchanger itself, right, as has been mentioned a number of times today, right, we wanted to get it right the first time. Although additive at the time was still very, fairly new for us, and we were learning, in everything that we did, we wanted to succeed. And we'll talk a little bit more about success on a subsequent slide, but success doesn't always have to mean hitting your objectives, right? If you're learning and if you're bettering yourself and your process, even from a quote unquote an opportunity, aka maybe a failure, there's nothing wrong with that. So while we wanted to get everything right the first time, we did not do that. I'll be very honest about that. But as long as we're able to learn and continue to move ourselves forward along our journey, that has to be defined as success. And again, I'll talk a little bit about that on a subsequent slide. Some of the performance characteristics, obviously, we talk about no powder entrapment, right? For a difficult geometry like a difficult closed geometry like a heat exchanger, powder entrapment is a huge issue. So that was important for us. Leaks on the primary surfaces, obviously, we cannot have the fluids interacting, and so that was important. And then, obviously, looking at some new materials, trying to reduce our NRE, right? So really trying to, through modeling, through simulation, reduce a lot of our efforts up front. Very, very important metric for us, and we were able to do most of that. So how did the team work? Again, we all understand the physics of additive manufacturing. I'm sure everyone in the room has great experience in that. But for us, one of the key learnings was, how did we break this down? What were the opportunities from an organizational perspective to really improve? And so if you think about some of our traditional, what we call silo-based manufacturing, engineering, hands off to design, hands off to operations, hands off to quality, et cetera. And it goes through the value stream in a very linear fashion. But for us, right, we knew we needed to break that paradigm. We knew we needed to change the way we did business. And so we really took a more collaborative approach, right? And so the graphic down below, right, where really all of the different functions, all of the different teams were interacting with each other on a real-time basis, right? And we kind of got rid of that linear nature of our previous operations. And so one of the things we were able to do, what I've sort of coined the phrase of mean time between success, right? We talk about mean time between failure typically, but again, back to my previous comments about success can be defined however we want to define it. And we defined it as long as we're continuing to learn, even if we don't hit our objectives, as long as we're continuing to mature our processes and better ourselves in the spirit of continuous improvement, that's a success. And so reducing that mean time between success, right? Reducing the time between iterations was very, very important to us. And so that last bullet of build, test, analyze, and repeat, we were able to shrink that time significantly from where we started when we first kicked off this project to where we ended. And so again, going through builds very much quicker, going through design analysis much quicker, going through simulations much quicker, very, very important. And then virtual collaboration in today's environment, right? As I'm sitting, thousands of miles away from all of you in Munich, the virtual world has unlocked, obviously, as we all know, as a result of the pandemic, more than it ever had been previously. But at this time, and again, in the 2015, 2016 timeframe, That was a new approach for us. Typically, we would have gathered the team all in one location. If they were traveling from afar, they would have lived in a hotel for months at a time. But back then, that it was very new for us to collaborate and work virtually, and we were able to overcome some of those early obstacles, and we've put those in place today. So I kind of think that through this effort, right, we were maybe a little bit better prepared for the world in which COVID has presented us than perhaps we would have been. And so we learned a lot about how to work, in a more collaborative way through this modem, right, through virtual aspects. So this is what the part looks like in its final form. This was published, in Metal AM, as I mentioned, back in the summer of 2019. You can certainly feel free to go look at the article. Has a lot of good depth and information that just not able to cover here in such a brief time. But again, thanks to our partners at Metal AM for preparing and publishing this article for us. And it looks like I may be missing a slide talking about some of our lessons learned. I do apologize. Let me touch on a couple of things, however. So a couple of things I wanted to touch on with respect to lessons learned. Again, talking about breaking the way the teams work, right? Talking about working more collaboratively, especially in a virtual environment. A huge success for us, a huge lesson learned for us. And it gets us through some of the early technology challenges, much quicker. So again, as we like to talk about, mean time between success, not mean time between failure. As I've challenged my team, especially for a new technology like additive, again, success is however we want to define it. And we're choosing to define success as no matter what the outcome is, right? If we're bettering ourselves, if we're learning from those quote unquote opportunities or failures, that to me is success. So when we define a set of objective criteria for a certain step, a certain build, et cetera, even if we come up a little bit short, as long as we're able to take those lessons and apply them and move forward in our process, move forward towards our objectives, again, we define that as success. And then, of course, lastly is, the use of some of the tools, right? Some of the tools, some of the physics-based models, some of the simulation tools that we did develop as part of this process, we are really able to exploit those now today, as we're now 4 and 5 years more mature in our AM journey than we had been at the time. So again, a lot of great learnings coming out of this, especially for a company like Collins, where we are so focused on thermal management, heat exchanger type products. This is a wonderful opportunity to work across not only then UTC, now Raytheon, work with America Makes, work with AFRL, and work with some of our external companies. So again, that collaborative nature that continues today across Collins Aerospace. So I think I'm about 1:50 early. So hopefully I've met that objective. Again, I do apologize that there was a slide missing, but hopefully I've shared with you some of our challenges and some of our learnings.
Absolutely, you did. Thank you so much, Bill Haddad. And we will be coming back to you for questions and answers in just a bit. And you saved us some time that we can use for that dialogue. So much appreciated. We now go to Jason Carroll at the power management company Eaton for our last presentation of a blueprint case here in this Americas section. And then we're looking forward to your questions and comments, ladies and gentlemen. So please send them to us virtually, or we'll take live comments in the room after we hear from Jason. The floor is yours, Jason.
Great. Well, thank you for having me, and good afternoon. I want to talk specifically about one product that we were leading on in the last few years with Additive, but I really want to talk about Additive in the context of driving product differentiation and what we see as the digital age of product development and how it's going to have a significant impact on our company. So if you don't know Eaton, we are an intelligent power management company. We are in everything from airplanes to cars to trucks and anything that moves electrons around the world. 85,000 employees based out of Dublin, Ireland, and Cleveland, Ohio. And depending on which way the winds blow of the stock market, we're anywhere to $50 to $60 billion market cap company with about $20 billion in revenues. Our additive journey began in late 2016, so we've got a much later start than many companies that you've probably heard from today. starting in Detroit, Michigan, with our Additive Manufacturing Center of Excellence, which still exists today, and has been driving the lead programs that have defined how we've delivered additive, not only to our manufacturing facilities, but to our product development teams around the world. Our focus, as many of the folks you probably heard from today, has been on aerospace, and is still a key focus for us today. And we have, as of 2019, started to deliver our first programs to our OEM customers in the aerospace world, and have now started to invest very heavily in our Charleston, South Carolina aerospace facility, where we're really seeing exponential growth in aerospace and a huge financial impact to our aerospace portfolio and growth. So additive has now really come full circle for us, and we're seeing significant impact in our aerospace, and now moving to our transportation business. Where we go from here, and I'll talk more about that holistically in a few slides, is we really look at additive along all of the different modalities, and where we're headed as a company spiritually and literally is using additive as part of system level design, in be it a stationary or mobile power systems. So anything from a inverter or a axial flux motor for a car to a very large power solid state transformer systems that we're designing today. So additive in all its different modalities is a big deal for Eaton, and how we create product differentiation at the system level, including looking at next gen additive that's coming out with different startups around the world. We're very active in all of them. And our approach has always been not centralized or distributed to our businesses. We have about 50 businesses, depending on how you count. We're somewhere between 40 and 50 businesses globally. And we always have strong connection between what we call our Eaton Research Labs, which are dealing with low technology and manufacturing maturity technologies, which is where additive was for us 6 years ago. And we are always co-locating people from our businesses with our research labs as early as the beginning of the development that we're doing. And then you'll see research folks on my team around the world where we deploy product into the field. So we always have a strong handshake between our businesses and research labs, moving from R&D all the way to full rate production. And as we move to full rate production, a lot of that funding then stays with our businesses. But again, the people that we have matured in our research labs tend to go to our businesses and continue to drive the exponential growth that we're especially seeing in our aerospace business. Just to give you kind of a high level view of how we look at additive, and especially from the research perspective, we really have 4 things that we work on at a high level to bring in new additive technology and validate it to the point that we feel proud and secure in putting a system into one of our plants. Obviously, process mapping is very generic, and you've heard about it, I'm sure, before. But we really look at how do we map out the entire variable space of a new machine. And the approach we take is to look at extreme value statistics, where we understand the defect populations at all the different process parameters. And we can do that very rapidly using CT scanning technology. So we can map a whole, say, a new EOS or SLM system, or even a polymer system, in a matter of just hours, by creating towers that have every combination of process parameters that you could think of in a new machine. And then ultimately that extends to ultrasonic fatigue, which is a key part of what we do at Eaton, which is we can validate the fatigue properties, the durability properties of a machine in hours versus months, and show real data that represents the process choices we may make in designing a part, as well as understanding the statistical variation in the machine, and either getting it out or being able to work around it from a design perspective. And that allows us then to validate a system and deliver it to our production facilities around the world and feel very confident. And again, we can do that in a matter of days or weeks versus maybe using conventional methods. It would take you months to years to do that. So it's a very key part of how we can quickly bring in new additive technologies, as well as the design rules for that additive technology, and start making a product and making money with new additive technologies as they mature very rapidly. So to give you just an example of the first part that we've publicly talked about, which is a launch of a ram air valve with AIDC, which makes the Advanced Jet Trainer Fighter for Taiwan. And this was a part that had 11 aluminum and steel parts associated with it in its conventional form. And we reduced that to one with additive. So I know Melissa talked about part consolidation as a big driver for sustainability. For us, it's a big driver for showing that additive, even it may be a slower process than conventional processing. The powder may be more expensive, but when you start to consolidate parts, you start to show real value at the system level. And that's where we find a lot of the value that we're driving and winning business with today. So in this case, aluminum and laser powder bed was the material and process that we used. And as I mentioned before, ultrasonic fatigue and validating not only the process parameters of the machine, but ultimately the life and durability of the product was done using non-conventional fatigue testing with our partners at the University of Michigan and Herwig Meyer, who's a world-renowned expert in fatigue and a friend of mine out of BOCO in Vienna, Austria. And so we're very proud and have published many papers on this. And it's been a very strong differentiator for us to achieve in just a few years what it took many companies nearly a decade to do to drive their first products into market and to start to kind of ride that exponential of growth, especially in our aerospace business. So that leads me to maybe a more provocative piece of what I talk about all the time to our senior leaders. I work for the CTO and I'm often talking to our CEO and board on where is additive, but not just on its own as maybe a process that replaces casting, forging, and machining, but where does it fit in this kind of new digital age of system engineering design? And so for me, additive is the manufacturing process that builds on what we call digital design, and I call mosaic materials, that when you add that with multi-modalities of additive, you can truly create extraordinary product differentiation. And as you think about that as a company, it leads you to that first pillar of digital design. And we've done a lot of work with the U.S. military in the last few years around this idea of, hey, Siri, design me whatever it is you want. And in a world where you're talking to your phone or to Google, if you will, to a simple UI, and the computer is designing the system for you in minutes versus months or years. And it's doing it by looking at materials very differently as well. We often talk about computational materials engineering. I look at it differently. I look at it in a world where in 20, 30 years, when someone asks you what material is your product made out of, you won't know what to say because we're not making things out of steel or aluminum or even conventional composites. The computer is going to create a mosaic of materials, not just one or two, but whatever, even at the voxel level, if you will, that's going to define the optimal outcome at the macro level. And so having a digital computational system where you can talk to the machine and have it design multi-scale with additive as the approach, or multiple additive modalities as the approach to create value, is really where the future is going. And so what we're doing at Eaton, and I'd love to talk more about it in the years to come, a lot of it's very sensitive right now, but we're designing power systems, be it solid state power electronic devices or other larger systems made from them, by combining additive with a lot of different material choices and letting the computer decide on how to lay it out to give us the optimal outcomes, be it a noise, vibration, and harshness, EMI, EMC, or other aspects of, say, a power electronic system. We're using this approach to really drive our investments and where we're pushing our engineering teams at Eaton around the world. But even more so, who is it that we're hiring? And so just hiring a mechanical engineer or materials engineer in the conventional way is really, to us, not where the world is headed. We need engineers who can design these systems that then ultimately design the products of the future for our company. So this is a very big area for Eaton. And again, it only happens because of additive and the maturity that we've developed in it. And it's something that we feel very passionately about will drive the future of power systems, and as well as, I think, the future of the industrialized world. So a very much an exciting area that I would love to talk more about in the future. And so with that, where are we headed? As I just mentioned, we started with taking a simple assembly and converting it to additive, taking the content out and driving value in materials that are pretty well known, like aluminum, Inconel, steels. And now we're actually using a digital platform to design the next generation of system products. So it could be a compact electric drive for an automotive or truck application. It could be, with that, an axial flux motor, a gear train, an inverter. We're using this design approach of digital design via user interface, mosaic of materials, and ultimately, different additive modalities to drive incredible differentiation in mobile power systems. And now we're turning our focus to stationary power systems. Could be a large energy DC-DC power system for charging your car. It could be a very large megawatt transformer. We're really starting to drive this approach and investment and bringing additive more than just a replacement for conventional processing, but an enabler for extreme product design and differentiation. And that's ultimately, where Eaton is positioned and headed very rapidly globally across all of our businesses. And with that, I think I finished with a couple minutes remaining. So thank you all for your attention.
Many thanks, Jason Carroll, for that very interesting presentation. We will now go to questions from the online audience and then from the audience in the room. And again, I'm going to just take them in order of the ones that have the most likes here. So I have a question that essentially goes to aerospace, which all of you talked about, aerospace. So I'm just going to put it out there, and then whoever wishes can give me a sign and speak to it. The question is this: the main examples we currently see being adopted in the aerospace applications are of non-critical, perhaps lower cost parts. When should we expect AM to be used at scale for more critical, higher cost parts, such as turbine or engine components? Maybe Melissa, get us started on that, and then if the others want to weigh in, you can as well.
Well, that's a really good question, and a lot of folks, I think, aren't aware of certain things. For example, GE has 30 additive parts in their 9X engine. These are turbine blades, very critical, right? And so we already are there. We do have the parts that I showed, similar parts to that, in the 787, those are structural load-bearing parts. In the satellite space, we have components. Now, these may not be in the high-rate production as we'll have in civil, but we have components that are holding the ion engine of the spacecraft, and these are as an assembly of 3 parts. That's about 1 meter long, and it's holding the engine. So this is, if it fails, it's the mission fails. So I think we're there, and at Boeing, we're shifting from the previous thoughts that we're just going to print a lot of parts, because you have no value there. The point is to find those cases. The heat exchanger example that was just shown. This is a wonderful case for additive manufacturing. Find multifunctional components that add value. We have a part that is a waveguide, a heat exchanger, and a structural component all in one. Things like that. Instead of just printing a lot of low value parts, find the applications that really provide a lot of value and not just optimize the part, but enable you to optimize the vehicle. That's really what we're looking for in terms of aviation. It would be if we could streamline the vehicle more by making the wings narrower, for example, or every other product that we sell has some way that we can optimize that through additive. And so that's where we are right now. We're really exploring those applications, and I dissuade everyone from just making these small sheet metal brackets that are very inexpensive traditionally. There's no business value there.
Mm-hmm. Thank you. Let me ask Bill or Jason if they would also like to speak to that.
I would agree with everything that Melissa
said. Sure. Sorry, Bill. We're not. Are you on mute by any chance, or do we just not have your sound turned up?
Not.
Okay. Go ahead. Now we hear you.
Mute. You have me now? Okay.
Yeah.
Thank you. Sorry about that. What I was saying was I agree with everything Melissa said. And for those of you who are familiar with Collins Aerospace, right, we're a very broad portfolio of products across the aviation industry. And all of our businesses at Collins Aerospace are engaged and efforting in additive manufacturing. And so, again, I gave a relatively simple example of the heat exchanger, but all of the businesses are applying additive within their product lines. And so we will see very soon some of the parts. I think the question was around, high value, critical infrastructure type parts. We will see those coming to market very, very soon. I think we've already seen them, as Melissa said. My colleagues at Pratt & Whitney, Melissa mentioned GE engines. My colleagues at Pratt & Whitney are doing a number of similar things as we speak. And again, across Collins, we are also developing some of those parts. I think the key is, as was said, not only in this panel, but in previous panels, finding the right applications, right? Finding the right parts where additive can really, as I like to say, solve a problem. That's key. Like Melissa said, don't just print a sheet metal part because we can. Go find a system, go find a component where the value of additive can help solve a problem that will drive ultimately customer value. That's kind of some of the focus that we have across Collins.
Thank you. And Jason, would you also like to add anything to that discussion?
No, I would agree with Bill and Melissa, and we're seeing that as well. I would say the next year to two, you'll see more publicly announced programs, especially at Eaton, where we've done very advanced flight critical systems with our OEM customers. So I think we're there. I think the maturity is there.
Thank you. And just staying with you, Jason, I have a question on ultrasonic fatigue that you talked about. And the question is this. The questioner says, can you elaborate? Are you using AI to make predictions of fatigue?
I would say yes, but ultimately it's more of using AI to design voxel by voxel. And so, the paradigm shift is this idea of monolithic material properties, where I make a chunk of something, I do fatigue testing like it's been done since the late 1800s, and I get a fatigue curve and I design to it. What ultrasonic fatigue allows you to do is understand how cracks grow at very low length scales and very slow rates, which is where really the physics needs to be understood to drive better product and better performance at the macro level. And so by understanding the crack dynamics and whatnot using ultrasonics, you can really understand the extreme value distribution of, say, porosity in a laser powder bed system. And once you know that, you could ideally design in porosity where there is no stress. And so you can start to define the product, or the fatigue properties voxel by voxel, not at a kind of a macro scale, with a very strong paradigm shift, especially in aerospace, where we want to do a quality control in kind of the mid 20th century way and design with monolithic properties. And additive obviously unlocks the door where we can not only have multiple materials, but one of the materials may be air. And so ultrasonic fatigue just allows you to understand the physics of that fundamentally at speed. And then you can use AI and whatnot to start to design from a multi-scale perspective what your part needs to be in the parameter space that'll give you optimal properties.
Thank you very much. And then going back to Melissa, another question essentially related to how you make the decisions about which parts you want to produce with AM and for which ones traditional may be adequate. So the question is this. As mentioned, the brackets are manufactured in the traditional method. Are there any parts which cannot be produced by AM? What are the reasons other than energy limitation? Is there a technical limitation that sometimes makes traditional better?
Let's see. There's a lot of parts you don't want to print, as I've discussed. You need to find applications that add value. The ones that you cannot print, they would be outside of the scope of the current machines, meaning that they won't fit in the platform of a current machine, or other parts that might require super high fidelity, maybe some really precise machining of a very small part, that sort of thing. But generally, it just goes around limitations of the machines, not necessarily the part. I suppose I could say if you have some sort of part where you have some fine features that are smaller than if you're using powder bed technology, then smaller than the melt pool width. Right, say so smaller than 120 microns or so, you're going to have trouble. So that's a limitation there on the small side, and on the big side, if you're using powder bed, it's limited by the size of the biggest machine, and in that case, You could probably go to a different modality like DED, directed energy deposition, where you can really have an unlimited size, but then you're going to have some post machining that you wouldn't otherwise.
Thank you.
Hope that answers.
Yeah, thank you very much. And now I have a question about materials. I'll just pose this to Jason, because you talked quite a bit about the potential for mosaic materials, I think you called them. So the question reads, titanium 64, IN 625, all very well-known materials. What are the main objectives and main motivations for using new and maybe exclusive AM materials?
For us, it's how do you solve those system level problems? So if you're trying to take and create a gallium nitride based power electronics device, you're really creating a thermal issue and EMI, EMC, and other issues at the system level. So then it really says, how can I put different elements from the periodic table next to each other within the rules of physics to optimize at the macro level those problems as I start to create unique devices. And I know Bill talked about thermal management. I mean, obviously you can come up with some very novel AI-based thermal management solutions with monolithic materials. If you open that up to a lot of different materials, you'll come up with even more interesting designs. And so for me, I don't think that technology is there yet for additive. You see people doing maybe 2 materials or maybe multi-materials in DED. But ultimately, the future is where we can put as many of them together as possible to solve the optimal macro response of the system in a financially correct way. So that's just, again, for us, that's where we're headed. We don't want to just think monolithically, although that's still where we kind of are parked as an industry. But the more advanced additive machines become, and the more ability to deliver multiple material solutions at each layer or each voxel, to me, that's how you really design highly differentiated products.
Mm-hmm. Thank you very much. Let me just go to the audience in the room now and ask whether we have live questions in the room. If you have a question, please raise your hand and we'll bring a microphone to you. Anybody? Not seeing any hands go up there. They may be dreaming about their afternoon cup of coffee because we're getting close to that time. One more chance, and is that a hand going up there? No? Yes? Okay, here we go. A mic is coming your way, I hope. Dear technicians, do we have a microphone? Hello. Can we get a microphone out here, please? Thank you. Here in the second block, in the third row.
Yeah, thank you very much. I have one question in the direction of Melissa from Boeing. In the beginning of your presentation, you showed a use case of a bracket made out of titanium, I think, and it showed that in every dimension of the sustainability criteria, it was better than machining the traditional part. I was just wondering, I recently read a report where this was also addressed, and it showed that when you machine a part, that a huge sustainability level still could be to recycle the chipped material, right? So I was wondering, is this been taken into consideration in this comparison? Maybe is there a reason not to recycle the chipped titanium, just to get an idea on that?
Melissa, was that well audible for you? Was it? Okay, good.
Yeah, it was. I could hear that fine, and thank you for the question. It's a really good question. So at Boeing, we have a big program where we do recycle all of our titanium scrap, and there's a lot of it, as you can imagine. And so we did, there's energy involved in recycling, right? It's not free. And in transport and things like that. And so that was also taken into account. But we still had the drastic change there. So we do recycle, and it's interesting to measure. I don't have this pulled out separately, but it's interesting to take into account the energy that is required to melt that and reatomize it and transport it. And it's good to do that, and we do it. It's good to do it. That's why we do it. There is a savings, but it doesn't negate the rest.
Thank you very much. We could take one more really quick question in the room, if someone, yeah, please.
Yeah, it goes also in the direction of Melissa. To get out the details about the sustainability aspects and so on, does this need a project to get all the details, or could you rely on tools where you say, okay, based on the tools, we get all the figures, data, and facts out of it and can count it together?
I'm not sure I understand the question. If I could repeat it, you're asking me to if we have a tool that can help us to understand the life cycle assessment. Is that correct?
Yeah, a tool where you can get out the details about the sustainability, that you say, okay, if we print this part in comparison to do it with milling, we have a sustainability, let me say, footprint for this part from XYZ and in comparison to the rest? Or is this more a project identifying step by step the logistics, the recycling, the energy consumption in each step? Is it more a manual project, or is this supported strongly by tools and you get it out for different parts very fast?
So part of it is supported by a tool. We use it's GABI software program for life cycle assessment. And that gives you a pretty good view of the traditional manufacturing modalities, whether it be, casting or machining. It doesn't have the information for additive, and so that's really manual, where we just go and measure and every single step along the way. So half of it is manual and half of it is automated.
Thank you very much. We're going to be picking up on exactly those points in our last session today, looking at sustainability considerations. So a good bridge to that. And many thanks to all three of you for those very, very interesting blueprint cases and for sharing your perspectives on so many different dimensions. Greatly appreciate your being with us, Jason, Bill, and Melissa.